Okay, welcome back, students. So we saw in the last class that we are given some observations. Okay, so we are drawing some observations from an observation vector. So it could be X observations taken at different time stamps. Suppose we have an observations. Now, depending on these observations, we need to figure out a detector which can tell me which hypothesis, either H0 or H1, is correct. Okay, we are looking at binary hypothesis testing problem. And in the last class, I also said that because these are higher dimensional observations, so what we are going to do is, if my X belongs to a region, let's say R1, then I decide my hypothesis H1 to be correct. If my X belongs to the region R0, then I decide my null hypothesis to be correct. Okay, and I need to figure out what should be my R1 such that I want to maximize my probability of detection given my probability of false alarm is less than equal to some threshold f. Okay, so I need to figure out R1 star by solving this optimization problem. Now, to solve this optimization problem, there is a very special theorem that is given, that is called as the Neyman-Pearson theorem. Okay, so Neyman-Pearson theorem provides exactly what should be this region R1 such that my probability of detection is maximized and my probability of false alarm is less than certain threshold value. Okay, so let's see how do we compute the Neyman-Pearson, how do we get the Neyman-Pearson theorem statement. Okay, so what we are essentially doing is we are trying to maximize the probability of detection. Can I write the probability of detection? Probability of detection, if you remember from our earlier class, integration over R1, probability of X given hypothesis 1 is correct, and then integrating over all points belonging to the region R1 such that my probability of false alarm, which is equal to, again integrating over R1, probability of now the X, the observations given my hypothesis, null hypothesis was correct, and then integrating it over this point, this is less than equal to certain threshold f. Now I need to solve this optimization problem, and if you recall from our earlier classes on optimization, I told you that to solve this optimization problem we need to write a Lagrange. So I'm going to write a Lagrange function. Now the Lagrange function will be a function of x and then a dual variable. Now there is only one constraint here, so the dual variable I'm considering is to be lambda, and that will be only one component. Okay, this is equal to PD minus lambda times PFA minus alpha. Alright, you can see that my optimization problem is a maximization problem. What we discussed was a minimization problem. So you can in fact do a minimization problem also with this, or you can also write an equivalent problem in terms of minimization. So let me write with that. In that case, it will be more clear. So I can write it in a equivalent standard form. So I can write it to be minimize minus PD. Okay, minus PD will be minus integral R1 probability of X given H1 dx such that now this will be PFA minus alpha is less than equal to 0. Okay. Now I can write the Lagrange in our original format. Now Lagrange is a function of x and lambda, and this is given by minus integral over r1 p of x given h1 dx plus lambda times pfa minus alpha. Let me also write pfa also. Let me expand this. So this becomes minus integral over r1 probability of x given h1 dx plus alpha times pfa is integral r1 integral over r1 p of x given h0 dx minus. Let me expand this. Let me combine these two together. This becomes integral over r1 probability of x given h0 lambda times minus probability of x given h1 dx minus lambda. So this is my Lagrange. Now you can see this is a minimization problem here. You can see this is a minimization problem here. So what I'm concerned is, what I'm bothered with is, I want to minimize this Lagrange. Lagrange is an augmented objective problem. It is augmented with the objective plus the constraint. So this is objective and this is constraint. So our goal here is to minimize the Lagrange. Minimize Lagrange. Okay. Why do we want to minimize Lagrange? Because our optimization problem here is, I've converted it to a minimization problem. If I were to use a maximization problem in form of Lagrange, then I would have maximized the Lagrange function. Okay. So now tell me, how can we minimize this particular Lagrange function? See, this is a constant. Suppose lambda is fixed. So this is a constant. Alpha is a constant and lambda is a constant. Okay, so it will remain fixed. What we can do is we need to find out r1, right? That is the variable that we require from this optimization problem. So this integral is evaluated for all values of r1. Okay, so let me write it down. This integral is evaluated for all x belonging to r1. Okay, r1 is what? Where h1 is decided. All right. So how am I going to minimize this Lagranges? If I, for each value of x belonging to r1, if I can minimize this value, then I can minimize the Lagrange also. So let me write it. For each x belonging to r1, each x belonging to r1, lambda times probability of x given h0 minus probability of x given h1. I want to minimize it, so I want to put it less than 0. This is what I'm going to do for each value of x in r1. All right. So if I solve this, let me take this to the other side and this in division. So you can see that it comes out to be probability of x given h1 divided by probability of x given h0 is greater than lambda. So if this happens for any x, okay, if this condition is satisfied, then x belongs to r1. And the question that you are going to ask is, how do we figure out lambda? Because lambda was the dual variable that we took, right? So lambda is computed. So as you remember from our earlier lecture, that this probability of false alarm, because these two, probability of detection and false alarm, are both increase or both decrease with the change in x or r1. So rather than this being an inequality here, it will be at the optimal point, this will be equal to, the false alarm will be equal to alpha. Okay, so if I do this, so if I take this point here, so probability of false alarm is equal to alpha at optimal point. This implies integral over r1 probability of x given h0 dx is equal to alpha. Now what is r1? R1 is set of points x such that probability of x given h1 divided by probability of x given h0 is greater than lambda. Okay, this is a set of R1. You see this condition. I'm just writing this condition here. Okay, so what is going to be my probability of false alarm? Probability of false alarm will be set of x such that probability of x given h1 divided by probability of x given h0 is greater than lambda. So I have to integrate over these set of points this particular probability and then equating it to alpha. So from here I'm going to get the value of lambda. I'm going to put this value of lambda here to get my condition. Okay, no, actually this is not required, sorry, this is not required. So lambda, what I'm going to get is by solving this equation. Okay, so what I'm going to do is I'm going to figure out first this ratio of the likelihood. So you can see this probability x given h1 divided by probability of x given h0. So this is what likelihood of h0, sorry, h1, and this is likelihood of h0, and this combined is also called as likelihood ratio. Okay, so I'm going to solve it is I have to take the likelihood ratio of h1 and h0 and then put it into this equation of false alarm probability, equate it equal to alpha, and from here I will figure out what is going to be my lambda. Okay, so let me write a complete statement for the Neyman-Pearson theorem, and then we will take up examples to show how do we solve such kind of problems here. So let me write the statement, the theorem statement. So to maximize PD, the probability of detection, for a given PFA equals to alpha, decide H1 if probability of x given h1 divided by probability of x given h0, the likelihood ratio, is greater than gamma, or let me write it lambda. I have taken a lambda where the threshold lambda is found from PFA is equal to integral x such that the probability of the likelihood ratio is greater than lambda, you have to integrate it over this point. The probability of x given age 0 times dx is equal to alpha. Okay, so this is the complete Neyman-Pearson theorem statement. So this is the Neyman-Pearson theorem, or it is also known as the likelihood ratio test, LRT. Okay, why it is called as the likelihood ratio test? Because this is the ratio of likelihood. I can also write it to be L of x, which is the likelihood ratio. And if the likelihood ratio is greater than some threshold lambda, then I decide h1. If it is less than lambda, then I decide h0. Okay, so let me take a very simple example to show how do we figure out the threshold values. Okay, this lambda, how do I figure out this lambda value? Okay, so let me take an example. I'm taking an example from our previous case that we discussed in the last lecture. So again, I'm considering my null hypothesis to be only noise. X is equal to W. I'm just taking one vector only, so X is only X0, you can say. W is again wide Gaussian noise with mean 0, variance sigma square. And in the alternate hypothesis, my X is 1 plus W. So what I have to do is, I have to solve this equation first. I have to solve this equation, probability of false alarm is equal to alpha. From here, I am going to get the value of lambda, which will provide me the LRT statistic. Okay, the likelihood ratio test statistic, lambda, that I'm going to get from this equation. Now, how do I solve such kind of equations? So, probability of false alarm is what? It is integral x x belonging to this range. Again, I'm writing the same thing. Probability of x given h0 dx is equal to alpha. Now, for this case, what are the likelihoods? So, as you know, we discussed in the last lecture, this is equal to 1 over 2 pi sigma square e power minus x minus 1 whole square over 2 sigma square, and probability of x given h0 is equal to 1 over under root 2 pi sigma square e power minus x square over 2 sigma square. Now what is the likelihood ratio here? What is the ratio coming out to be? So if you divide these two expressions, what you're going to get? These two are going to cancel, and some part of these are going to cancel, so it will be minus 1 over 2 sigma square x minus 1 whole square minus x square. If you expand this further, you are going to get e power minus 1 over 2 sigma square. This will be 1 minus 2x. All right, or further simplifying, it is equal to e power minus 1 over rather, let me take it inside, so it becomes x over sigma square minus 1 over 2 sigma square. Okay, so this is the likelihood ratio that I'm going to get. Now let me suppose that as we took in the last class, sigma square to be 1 here. So in this case, if sigma square is equal to 1, so this likelihood ratio turns out to be e power x minus half. Okay, so coming back to our expression here, my probability of false alarm is equal to, I'll integrate over x such that my e power x minus half is greater than lambda, and this probability is 1 over under root 2 pi sigma square is 1, So I can remove it. E power minus x square over 2 dx. X is a scalar, so I can remove the vector sign here. And this is equal to alpha. So now I have to solve this equation here. Now again, let me further simplify. What does this mean here? So if I solve this equation, so e power x minus half is greater than lambda. Taking log both the sides, I can get log of lambda is less than x minus half, or x is greater than half plus ln lambda. Let me write it to be, let me take this to be lambda hat. So when x is greater than lambda hat, then this condition is satisfied, where lambda hat is this point. Okay. So what I can do is I can write this particular expression, probability of false alarm, to be integral from from lambda hat to infinity 1 over under root 2 pi e power minus x square over 2 dx. This is equal to alpha. And as you recall from our earlier class, that this I can write it in a q form, and this is q of lambda hat is equal to alpha. Now, depending on the value of alpha, I can get lambda hat. Lambda hat is equal to q inverse of alpha. And this is my statistics. So how am I going to decide h1? So overall, if I write h1, I will decide if you see this expression here, if x is greater than lambda hat or q inverse of alpha, then I'm going to decide h1. Otherwise, I'm going to decide h0. All right, so let me do a quick revision of what we did in this particular case. So this was our problem. We had two statistics. My h0 and h1 are given. All right, and so what I did is I first have to figure out what is going to be my lambda here. So for that thing, I have to solve this equation, the probability of false alarm equation. Now to solve this, I need this particular expression here. So I figured out first the likelihood ratio functions. Solving this, I got this condition here, which is x should be greater than half plus ln of lambda. Okay. Now after taking this into account in the probability of false alarm equation, I have solved this equation and figured out what should be lambda dash, and then depending on this lambda dash, I have drawn my statistics. Okay, so this is the basic procedure of solving a particular detection problem using the Neyman-Pearson equation here. It is very simple. You have to just solve this probability of false alarm equation, where you are just taking the likelihood ratio test here, and then you are making this useful to get the value of lambda, which you use it in your sufficient statistics.